For the final worked example of the mechanics module, we're going to use everything we've learned so far. The question here is, how high should you start in a kart in a Luna Park to make a looping? So suppose you're in a little train on a track that's going to make a loop. How high should the train start such that it actually completes the loop? We're going to ask for the minimum height and also see if it's possible to do a higher height, or whether that would not work at all. So naively, you might think that, well, if we want to make the loop, also first, as usual, let's sketch the situation. So we're going to be on a track, and that track is going to make a looping, which of course should be a circle. I'm not very good at drawing circles. And then it should continue. And so our kart is going to be some block that is going to be here at the start. It's going to slide down, pick up speed, going to go with some speed here, going to go up through the loop, upside down, down again, and then out of the loop. Well, you might say, well, if you start at equal height as the loop, as the height of the loop, then of course you should reach the top of the loop, which is true. But unless you're attached to the rail, at that point you would fall down. So clearly you need to start somewhere higher. So to properly define our system, let's assume that the loop is a circle which has some radius, capital R, and we're going to start here the kart at time 0 at some height h, and we want to know how high should h be so that we fully complete the loop. Now, to complete the loop, of course, what we need is for our kart to be in a circular motion when it goes through the loop. So what we need is that at the top of the circular motion, the forces on the kart, right? So in this top situation, it should be in a circular motion. Right? The net force on this kart should equal the centripetal force. Now, what are the forces acting on the kart? Well, as always, there is gravity. And there might be a normal force from the track. Now, this is what we don't want, usually, because if you have a normal force from the track, then there's going to be friction between the kart and the track track is going to wear down. So in an ideal situation, we're going to have only gravity as our net force at the top of the loop. So gravity should then equal the centripetal force. Now we know the magnitude of the gravitational force, which is the mass of the kart times the gravitational acceleration. And we also know the magnitude of the centripetal force, right, which is the mass times the velocity squared divided by the radius of our circle. So what we find by equating these things is that, as usually is the case, the mass of the kart is irrelevant, and we find that v squared over r is equal to the gravitational acceleration, or that the velocity at the top should equal g times the square root of g times r. Now, for the velocity at the top to be this magnitude, what should be the height that we start off at? Now, if we start from rest, the energy that we have at the start, of course, is only potential energy due to gravity. So here what we can say, well, if we look at this position, we have only potential energy, which is m times g times h, right? And we compare it with, again, this position, where we now have two forms of energy. Right? So this is u1, u2 plus k, which is, well, we're now at a height of 2 times the radius, plus we have a kinetic energy given by half of the mass times the velocity at the top squared. Now, again, the mass is going to drop out, and we can substitute the velocity at the top that we've just calculated. So what we find is that g times h equals 2g times r plus a half times, well, we have the square root of gr squared, so that's a half times g times r. And again, also the gravitational acceleration is going to drop out. And what we're left with is that the height should be 5/2 the radius of the loop. And we see that it doesn't matter whether we're on Earth or on the moon, the height should be the same. So, as per usual, we check if our answer makes sense in two ways. One way is, do the units work out? Well, on the left-hand side we have a height, which we measure in meters. On the right-hand side we have a radius of the loop, which we also measure in meters. So yes, the units work out. And if we would increase the radius, we would of course expect the height also, the necessary height also to increase. What would happen if we start at a lower height? Well, then our velocity would not be high enough and we would fall off the track. If we would start at a higher height, then our velocity at the top would be higher than the minimum necessary velocity, so our centripetal force would be larger, which means that the net force is larger than this required quantity. Of course, the gravitational force is not going to go up, so the only way that can happen is if the track is pushing on the cart. And so indeed then we would get a normal force from the track on the cart, which means that we would also have a friction force and we would get wear and tear, and eventually something would break and you would still not be happy. So next time you go and take a ride in a cart that's going to make a loop, do take your measuring stick, measure the radius of the loop, and compare it to the height that you're let go of. Now hopefully you've seen that indeed we have used everything in this example. Right? We started with making an observation about circular motion and the centripetal force. We used a force balance to figure out what then the velocity should be, and we used an energy balance to relate that velocity to the required height. So all the pieces of mechanics can nicely come together in this example and in many other examples, ranging from the motion of the planets to subatomic physics and way beyond that.